All right. Well, thank you, Joe, and thank you to the entire first row, actually, for inviting me. It's been very well taken care of here and at Marquand House. All right, let me first tell you what brought me to the question I'm going to talk about, and then, well, I'll give a proof, but I'll also advertise this shape invariant I'll talk about a lot, quite a bit more. So I think it's very interesting, and it hasn't been getting the attention I think it should. All right, so, well, there's one thing everyone here knows. It's that if you have a sequence of symplectic diffeomorphisms and let's convert this uniformly to diffeomorphism, then and there's a lot of proofs of that theorem at that global level. First one by Eliashberg using wavefronts, and then Gromov gave another proof using his Gromov alternative and non-squeezing. There's a couple other more modern proofs of that as well, but they're all for diffeomorphisms, and a stronger statement is the same thing for embeddings. Let's see, we have a ball. And their embeddings. And they're all symplectic. Then the same statement holds for embeddings. And as far as I know, the only proofs of this statement use capacities by characterizing symplectic diffeomorphisms by capacities. So this second theorem implies the first one, and that doesn't have quite as many proofs as the embedding version. And the key to that is that if we have these embeddings, phi then phi star of omega is plus minus omega 0 if and only if phi preserves the capacity of ellipsoids. And from that statement, it's not too difficult to give a proof of this theorem, and then eventually the rigidity of diffeomorphisms. So that's probably the modern proof, or that's how, or the most general statement of rigidity. And I guess my first remark, and that's kind of important later, is that these capacities can't distinguish symplectic and anti-symplectic. It's one of the axioms that of capacities, but for me, in essence, that if you have an ellipsoid, you can always find an anti-symplectic diffeomorphism that maps it to itself. So that's, in essence, the reason why you can tell the things apart. My original motivation for what I'm talking about today is to do something similar for contact embeddings. And the first problem is if we look at a contact embedding, we use something like U to B, contact embedding. And then there's a lift. To the so-called symplectization, you add an R factor, which is simply defined as contact forms here. So these are co-orientable. I'll come back to that later. So there's a lift, and that's a symplectic embedding. And one can try to just use the same proof using capacities for that symplectic embedding. The problem, however, is that the capacity it's always infinite. It's actually not too difficult to see because you can just rescale the R plus factor. You just multiply by S. That rescales the symplectic form. This is, here we have symplectic form dt alpha 2. There's dt alpha 1. And that rescales the symplectic form, and then you just embed a small ball, which exists by Dabou's theorem, and then you actually get that the capacity is S squared times the capacity of that small ball, and then S goes to infinity. Did it just get dark in here? Did you see the capacity is infinite? So that's not going to work. Well, maybe I should not claim that capacities can't work at all, because people always come up with something new. But this direct approach where you lift a contact embedding to a symplectic embedding and then look at the capacities of these, of the lift of the contact manifolds, that doesn't work because the capacity is infinite. So you can't actually say anything meaningful. All right. What I'm going to use instead is the following. That if we have an embedding then phi is symplectic if and only if phi preserves the shape of what I mean by that statement is that a symplectic embedding preserves shape, and then it's enough to preserve the shape of small sets of small Lagrangian tori, and then you get the converse. And then that's what I want to prove. And for that, I'm going to have to tell you what shape is, but that's what replaces this third theorem for capacities. And that does generalize eventually to contact embeddings. Now, that's what I'm going to explain. And one thing I want to point out before I start saying more about that is, for the capacities, you look at ellipsoids. So in the proof of theorem 3, you just always look at capacity of ellipsoids. That's enough. And the role of ellipsoids is played by small neighborhoods of Lagrangian tori. So I'm looking at Dabou's theorem up there in theorem 3, and what you use here is Dabou-Weinstein, that you have canonical neighborhood of an embedded Lagrangian torus. That's what's going to play the same role. All right, what's the shape? So I want to start with exact symplectic manifold. I'm going to assume there's no boundary, because boundary is always causing problems, but I guess you can just look at embeddings that stay away from the boundary, and I could make similar statements. The shape is, so we have Ln n-dimensional manifold. It's closed. And then we'll look at embeddings. I pick some homomorphism, and then the shape. And then we'll look at all the Lagrangian embeddings. Of a certain shape and size, so to speak. So you look at all the Lagrangian embeddings whose homology, whose action on homology is fixed. It's some homomorphism. And then if you pull back the one form lambda, you get some cohomology class on L. And we'll collect all these cohomology classes. All right. I want to do some examples just to illustrate what that looks like. But let me first make maybe a couple of remarks. The shape can be empty. But often it's not, so that's what we're going to look at later. And the second thing, it's defined only up to translation. So what I mean with that, if I pick a different lambda with a different primitive, so this is closed one form, then f star of lambda prime is just then I just translate this whole set by some fixed vector in the first cohomology of L. So it's not defined as its set itself, but there is some freedom of translation. But and here's the first time where you see that why I want to fix this action on the this map on the induced this induced map on homology, because then this is always the same vector, so it's a translation by a fixed vector. Otherwise, this could be anything. So I need to fix this induced map. And then there's some freedom of translation, but in practice it doesn't cause any problems because it's some fixed vector, and that can be dealt with. Okay. All right. All right. Now, I want to say that before I start erasing anything, if I make this R small enough, then the image is contained in a small neighborhood of a point, and on a small enough subset on every manifold, the symplectic form is exact. So even though this is a general manifold, locally omega is always exact, and that's how I'm going to apply this whole shape invariant. So this is only defined for exact symplectic manifolds, but locally every omega is exact. So as long as I make R small enough, I can assume that in this theorem omega is an exact form. In fact, it's just going to be R to n. Say again, please.
The locally 8 of the one of them.
Exactly. Yeah. So here, so, and then that's of course 0, and that's a problem because then the invariant doesn't tell me much, and I'll come back to how I fix that later. So the ambient manifold of an embedding really plays a big role because it tells you something about what tau is. What this. So I'll come back later. But exactly that's a problem. But if I define this correctly, it's not a problem. But I'll come back to that in a second. All right. Let's see. Maybe we should. And I should probably say at some point, so all I need in this talk is that L is Tn, so I'm going to implicitly assume that and just drop L from the notation. So I'm only going to look at embedded tori. Then if tau is surjective, then the shape is open because you just take a point in there. It comes from some Lagrangian embedding. And you take a Darboux-Weinstein neighborhood of that. And if you translate by closed one form, and I look at then I just get so this Lagrangian embedding has this period, and if tau is surjective, I get an open neighborhood of the shape of the period. This thing is called the lambda period. I get an open neighborhood of that point Z. All right. Here's an example due to Virchow-Bourg, although he didn't use the same language. But if you look at if tau is 0, then and by irrational just means that actually I'm looking at Tn, so the homology is just Rn, and irrational just means that the components of this vector are rationally independent. If it's irrational, then you can embed. So you can, well, maybe I should say it. So you can find some matrix. So A times Z is Y, and Y is small. And just take a split Lagrangian torus that embeds into and so that I star of lambda is Y. And then I can just look at A inverse transpose composed with this one. So if tau is 0, then you can find Lagrangian embedding of any irrational period into a small ball, and that sits inside U as well. So if the homomorphism is 0, as you pointed out earlier, then this invariant isn't much good because there's too many things. All the rational periods are inside the shape. All right. One last one. It's more of a theorem. If you look at a subset of the cotangent bundle of a torus and just look at the canonical embedding of the zero section, and you take that as the homomorphism tau, the induced map here, then the shape of this set is exactly this set A itself. Well, I guess this part is pretty obvious because you just embed the torus as Tn times A. So you just look at and the converse of that is actually just Gromov's theorem on intersection of exact embeddings with a zero section. So what you do is you look at some embedding and you assume that the period of that embedding is A. And you want to show that A lies inside the set A. Well, you just can look at we should put negative A here. But this would just mean translation the fiber by the vector negative A. So you just look at the fiber of the tangent bundle and you just translate by the vector minus A. If I look at the pullback here, I get this is just A1 times dq1 plus A2 times dq2 and so on. And this is just A minus get 0. So that one is an exact Lagrangian embedding, so it must intersect the zero section. But if this embedding here intersects the zero section, then this one here has to intersect Tn times A. So xa is in Tn times A. So A is in A. That tells you that the shape is exactly the set A. So Gromov's theorem translates to this theorem that the shape of a subset Tn times A is exactly the set A. All right, and that's what we're going to use to prove that fourth theorem. All right. Bless you. All right, where are we at? Okay, just. It's pretty obvious that the shape is a symplectic invariant, because if I take any embedding of Tn into M1, I just look at composition with that symplectic embedding, and that's again Lagrangian, and it has exactly the same period. Okay, so it's a symplectic invariant, and my claim is that it actually, the converse holds as well. If you have an embedding that preserves the shape, then it must be symplectic. All right. Let's see. Okay. So suppose I have M1 and M2, and I have this embedding between these two symplectic manifolds of the same dimension. And I say that phi preserves shape if for all U and M1 and V and M2, so that U bar and M is compact, and phi of U bar is in V, we have I should have mentioned something else here. So this is up to translation. So I should say it's contained in this plus B, and this vector B here is just tau of phi star of lambda 2 minus lambda 1. So inclusion really means up to a fixed translation, but that vector B really depends only on which one form lambda 1 I choose to compute the shape. So it's not really a great issue that this inclusion holds up to that fixed translation by some vector. And the same thing here, so I should say up to translation. And my comment here is kind of going back to a question something you brought up like 5 or 10 minutes ago. If I said that shape is preserved if the shape of M1, so if I made this definition just with M1 and M2 here, and M2 is just R2n, then this is automatically 0, and I'm really not getting much. But if I want to preserve the shape of all subsets U and V, then I can, in practice, it's just going to be a tubular neighborhood of a torus, and that has a lot of homology. Okay. So if I don't do that for all subsets, then M2 is just R2n, and you don't get any cohomology, and there's nothing going on. And exactly. So in practice, what this is going to be the U. I take an embedded Lagrangian torus, and I take a tubular neighborhood, and then look at its image, and I take a tubular neighborhood of that. And those are going to be my sets U and V, and they have a lot of cohomology, and then there's a lot of invariance. And it doesn't work if you just look at the ambient, at the entire manifold M2, because there could be, or in practice it's R2n, and then this homomorphism is 0, and then you have too many elements in the shape, namely all the rational numbers, all the rational vectors Z. All right. Okay. Let's see. Okay, and the reason I defined, I require that the closure of U is compact lies in V is simply so that this following proposition becomes obvious. If you have phi k and phi, which are embeddings from M1 to M2, same dimension again, and phi k preserves shape, and phi k goes to phi uniformly on compact subsets, then phi preserves shape. And the proof is simply you that phi k of U bar is in V for k large, and phi k is homotopic to phi. And the assumption that phi k preserves shape just means that this inclusion here holds with phi k here, and since they're homotopic for k large enough, I just get phi star here, and the limit preserves shape. So this is the equivalent of capacities being the property of preserving capacities is preserved under uniform limits, and that's the equivalent of that one over here. So, and that's what makes the following thing possible. And since I raised those a long time ago, I'm just going to say really quick what those numbers were. This says that an embedding is symplectic if and only if preserves shape. Then that property to preserve shape is preserved by uniform limits. So the limit also preserves shape, and therefore it's symplectic, and that implies that symplectic embeddings are C0 rigid. And then you have the same thing for diffeomorphisms. So that's the game plan. That's how you get the rigidity statements I stated in the very beginning. So what I need to prove is this theorem 4, and then the proposition implies that symplectic is C0 rigid. All right. I sometimes tend to talk all fast, but just feel free to interrupt me if I'm saying something that doesn't make any sense. Otherwise, I'll just keep rambling. All right. Looks good. All right, then let me show how you prove this theorem that an embedding is symplectic if and only if the shape is preserved. And the first, I guess I should just call the lemma, is that if we have in embedding then phi is conformally symplectic if and only if phi preserves Lagrangian submanifolds. Okay, I'm going to give a sketch of the proof, but when I first thought of it, I thought it was something that definitely should be true, but I couldn't find that statement written anywhere. So I'm going to tell you really quick how to prove that, but I think it's actually just linear algebra. So there's not much to it. But yeah, I was surprised to maybe I didn't look in the right places, but Google told me that no one's stated that before, so I don't know. I'm sure many people know this already. All right. And preserves Lagrangian submanifold just means if you take a Lagrangian, you look at its image, it's again Lagrangian. Okay, so what you can look at is symplectic is so this direction is clear. If something is conformally symplectic, then it preserves Lagrangian submanifolds. So I want to prove the converse. And since this is just a pointwise property, it's enough to look at R2n. Now look at the pullback of omega 0, and it's some 2 form. And there's some other functions over here. dqi, which dqj. And what I know is that Lagrangian submanifolds are preserved. So if I look at, pick the vectors, say dpi and dpj, they span an isotropic subspace of R2n. So I can expand that to Lagrangian basis. And that in turn I can expand to a symplectic basis. So I can find a torus and then by assumption 0 is phi star omega 0 dpi dpj, which is just fij at 0. And there's nothing special about these two vectors, ddpi and ddpj. I can do the same thing with dpi and dqj and dqi and dqj. So this is also 0, hij 0 and gij 0 if I is not j. So that just means that, and then I think last but not least I need to pick something like dpi plus minus d what do I need to take here? Then I get that gii is the same as gjj at 0. So phi star of omega 0. It's just some function times omega 0. That's just linear algebra, and then this is closed, so g is constant. Okay. And of course, that's where I need that n is positive. N is at least 2, sorry. Because if n is 1, then all one-dimensional manifolds are Lagrangian, and then if too many, and this obviously can't be true, and what it breaks down is just that if the dimension is 2, then omega being closed doesn't imply that g is constant. It's just a volume, an area form. So that's where you need that n is greater than 1. That's not a big problem, though, because if n is 1, we're not really talking about symplectic geometry. It's just area preserving, like an area form, and all these theorems I stated earlier are actually quite easy to prove if you're just looking at surfaces. So the real issue is if n is greater than 1, and then this works. Okay. Let's see. Actually, the same thing is true if I look at two symplectic forms. If they have the same Lagrangian submanifolds, then they're conformally the same. So one is a multiple of the other. It's the same idea. I don't need that, but I thought it's nice to point out. All right. Just one more thing I need. And that is that earlier I said that capacities, they can't tell a symplectic embedding apart from an anti-symplectic one. And the shape can do that. And what I mean by that is the following. If phi is an embedding, if an embedding preserves shape, then and it's conformally symplectic, then this constant must be 1. And the proof is I can take an embedded Lagrangian torus in M1 and look at the two-blind neighborhood of that, and its shape is exactly A. So A is this is the neighborhood of the torus, and the shape is exactly A. And since phi star rescales the symplectic form, it will also rescale that set A. So the shape of that is essentially just C times A. I'm skipping some minor details, but it's the same. So I just look at a Lagrangian embedding, and then I compose with phi, and that rescales the period by the factor C. And I just need to pick some open unconnected subset. If it's a proper set of Rn, then C or E can't be less than 1. And if it's not symmetric about the origin, then it can't be -1. And if I just look at the local inverse, then it can't be greater than 1 either. So that's the gist of it. That since I know exactly what the shape looks like for certain subsets, I can say that if you rescale the symplectic form, then it can preserve shape. So if it preserves shape, then conformally symplectic means symplectic. Okay. All right. Okay, that's all the preparation I need. Let me show you how to prove that main theorem. So what I can assume is that n is more than 1, because otherwise it's an area form, and I can prove things quite directly without using symplectic geometry. So that's quite easy to do if n is 1. Then I can also assume phi star of omega 0 is not some multiple of omega 0. So I'm assuming that phi preserves shape, and then C can't be anything other than 1. So what it tells me is there exists some point there's in the neighborhood U of x, so that there exists Lagrangian torus Because, well, if it's not conformally symplectic, then there must be a Lagrangian submanifold that's not preserved. That's, I don't know if I erased that already. Write this lemma over here. So if I assume that the embedding is neither symplectic nor conformally symplectic, then there must be some Lagrangian torus that's not preserved. So the image of it is not Lagrangian. And the picture looks as follows. I have something here, and then I put phi, and I have something over here. And this is Lagrangian. This is not Lagrangian. And I'm going to take some neighborhood here. This is going to be my u, and some neighborhood over here. This is v. And what I'm going to show is that if so this vector here is in the shape of u, and if I can show it's not in the shape of this neighborhood v, then phi doesn't preserve shape, and that's the converse to the first part of theorem 4. So if it's symplectic, then it preserves shape, and if it doesn't preserve shape, if it's not symplectic, then it doesn't preserve shape, and that's enough to prove the theorem. Okay, I'm kind of sweeping something on the rug a little bit, namely that this is defined up to translation. So what we have over here really is z plus some vector b, and b is but that's not really an issue. So instead of showing that z is not in here, I just show that z plus b is not in the set where b is exactly this vector here. So it only depends on the one forms I choose here, and then on phi, and this is fixed as well. So that's not really a problem in the proof. All right, so what's the neighborhood v that I need to construct? Well, there's a theorem of Laudenbach and Sikorav. That tells me that there exists a vector field f, so that that is nowhere tangent So more generally, if you have a manifold that's not Lagrangian, then you can always find a Hamiltonian vector field that's nowhere tangent to that submanifold. So for Lagrangians, that's of course not possible because the L is closed. So what am I trying to say? Let me put it that way. So in other words, a non-Lagrangian submanifold can be displaced immediately. So you have this vector field, which is not tangent to it. So the flow after time epsilon for every small epsilon does not intersect that original manifold L. So if It's everywhere non-Lagrangian here. Sorry, it's just at a point. So just at a point. So, and I guess I never mentioned that. Yeah. So just at one point's enough. Yeah. Yeah. Okay, but that's all I know about this L anyway. That like at least at one point it's not Lagrangian, and that's enough to construct this vector field. And actually, the proof doesn't use much symplectic geometry up to the very end. You construct some section, and which is you have some section of the symplectic dual of the tangent space, and then you construct some function, or they construct some function, so that df of x is never 0, and that just translates to, of course, to and that means that the vector field is not tangent to L, because if it was, then then this symplectic pairing would have to be 0 somewhere. But yeah, most of the proof doesn't use symplectic geometry. Just in the end, you use that simple fact. All right. What does it really mean? Is that means for every epsilon there exists a neighborhood n epsilon of L.
You mean for all epsilon?
Yeah. L is this thing over here. So that the displacement energy of n epsilon is less than epsilon. So we look at this L here. You take your vector field and you flow for a very short time. So it has very small Hopf energy, and then L doesn't dissect itself, and then by compactness you just pick some neighborhood of L that also doesn't intersect its image. So you move L away a little bit, and you take a small neighborhood here, and that is displaced from itself. And actually I can just cut it off. I can cut off the function, what I call it over there, f. I can cut that off in the neighborhood as well. And so this Lagrangian, or this n epsilon, can be displaced with energy less than epsilon, and the whole isotopy, I might as well assume, is supported in some small neighborhood of everything that matters here. So everything happens in a small neighborhood of L. Okay, so this n epsilon has small displacement energy, and I can find such an n epsilon for every epsilon. And now I have different choices. And since I have only a couple of minutes left, I'm going to make one. I can assume that Z is rational. Because I pick some Lagrangian torus here that exists. So I have my Z here. If it's not rational, I'll just perturb it a little bit by a closed one form. And that's going to be have period small perturbation of Z. So then I get something that is rational. So that's quite easy, because I can just look at the original embedding and then compose with a closed one form. And that was one of the examples I mentioned at the very beginning. All right, I can assume Z is rational, and then I guess I'm going to have to make some choice again. And so I'll just tell you what Sikorav proved by Gromov compactness. I'm going to write that and comment on that a little bit more. there exists a non-constant holomorphic let's see. I'll explain those things in a second, so that the area of D is let me see, what's the inequality? This one goes to 0, so it's less than equal here. So what do all these things mean? This L prime is the suspension of L. So if I look at this vector field XF, I get a Hamiltonian isotopy of L. And I can look at the suspension of that, which is just going to be something in R to n times T star of S1. And this number here is, up to some small estimates, twice the displacement energy of, or twice the maximum of this Hamiltonian F. And then if delta is small enough, I get this non-constant holomorphic disk. And its boundary lies on L prime. And the period of L prime is actually the same as the period of L. And since integrating over D is the same as integrating lambda L, so we just get some cycle here. And here we have so if I should have said one more thing. So I assume I have Tn into L and J star of so here I just get Z of H1 of Tn Z. But what that means is that this is greater or equal to the generator of I should wrap that up. So this number lies in this image here, so it's greater or equal in the generator, which is a positive number for rational Z. So the displacement energy has to be, or half the displacement energy has to be greater than this generator here. But this I can make as small as I want. This goes to 0. If I make epsilon small enough, and that's a contradiction, so such an embedding with period Z can exist. And that wraps up the proof. Okay, at some point I was dreaming about talking about the contact case, but that's not going to happen today. So I'll have to stop here. Thank you. Thank you.